Okay, in this video we're going to look at some applications of geometric patterns. We've already seen one before in our previous unit when we looked at exponential functions. We looked at compound interest, so we're going to review that and then take it a step further. So basic situation here, if we have a $1,000 deposit into an account that pays 4% interest, and let's suppose that it's compounded annually. That means you get the interest added on just once a year. Well, this is a geometric sequence because think of it as, okay, we're starting with 1,000, all right, that's our first term. If we were to, first of all, understand that the common ratio would be 1.04, okay, because we have to multiply by 1.04 to get the next term. That's how we would be adding on 4%, okay? So the next term would be 1,040. If you took that amount and multiplied by 1.04, you'd get 1,081 and 60 cents, okay? If you took that and multiplied by that number again, you'd have 1124.86, all right, and so on, okay? So it's important to understand here that we're talking about our first term of 1,000. The common ratio we said is 1.04, but now we're going to write a formula, but in our formula, n is going to represent the number of years of growth. Okay, so in other words, if A represents the amount we have in our account, okay, we're starting with 1,000, okay, and our rate we said is 1.04, and then we're just going to raise it to the n. All right, that's how many years of growth we have. So when n is 0, that means we're starting with our first term of 1,000, right? There's $1,000 in the account. When n is 1, that means we have 1 year of growth, okay? So please understand here that n is not the term number in this case. N is corresponding to the number of years of growth, okay? Let's look at a more complicated situation now where our interest is compounded more than once a year. All right, so we're talking about now interest being compounded more than once a year. Now, this is a formula that is not given to you, so you're going to have to commit it to memory. So this A represents the amount of money that we have in the account, all right, after time has gone by. P represents the principal, and the principal is really talking about the starting amount. All right, so in our previous example, that was the 1,000, okay? Then we're going to have 1, all right, so this is all times, 1 plus, okay? Well, this R, all right, corresponds to our rate as a decimal. So before we said the rate was 4%, so we turned it into 0.04, and then we added it on to 1, and we got 1.04, okay? But now it's being compounded more than once a year. So n, okay, which shows up in a couple different places here, this represents the number of times that interest is compounded. That just means applied, okay, to your account in a year. So it's the number of times interest is compounded in a year, okay? If interest is compounded monthly, then our n would be 12. If interest is compounded quarterly, then n would be 4. And then finally, this t is our time in years. So this is representing the number of years that we're going to let the money sit there and accumulate interest. All right, let's look at an example. All right, so we're going to keep the same numbers from the previous example. We're talking about $1,000 that's invested. There's a 4% annual percentage rate, so APR, okay, for annual percentage rate. But we're told that it's compounded quarterly, okay, so the interest is going to be applied every quarter. We want to know how much do we have after 10 years. So let's fill in our formula here. We're starting with 1,000. We have 1 plus. We have 0.04, okay, that's the 4% of the decimal, divided by 4. So it's being broken up into quarters, so we're taking that rate and we're dividing it by 4. Now, if we're taking a year's worth of interest, dividing it by 4, and we're looking to hang on to this over 10 years, you're going to have 40 different periods of that interest being applied to your account. So we said that up here you're going to have your 4 times your 10, that's your n times your t, so that's really your 40, okay? So when we write this out, we have 1,000 times 1.01, that's what we get when we simplify the inside, raised to the 40. Okay, so again, this 1% that we see here on the inside, that's really being applied 40 times. Okay, so when we throw that into the calculator, we're going to end up with 1,488.86, and we're not going to bother with 3 sig figs here. If we're talking about money, it makes sense to just go to the nearest cent unless you're told otherwise. Okay. All right, and finally here, when it comes to compound interest, what if our interest is compounded continuously? And this is actually what happens in the real world. Interest is not compounded once a year or monthly or quarterly or daily, okay, or weekly or whatever. It's actually compounded every millisecond. All right, so think of it as n is really infinity, okay? So if it's compounded continuously, we actually have a different formula to use here, and it is A equals P times E raised to the RT. So we call it PERT, okay? So the variables still represent the same thing. Now you would think that it would make a huge difference if we were compounding the interest every millisecond. Well, let's see what happens. Now E, of course, is our number. I don't really need parentheses here. Okay, we'll just show that it's times E raised to the rate, which is, again, 0.04. Let's use the same numbers as the previous example, and suppose we're allowing it to grow for 10 years. So if we were to throw this into the calculator, we would get something very close to the other amount. It's only about a $3 difference or so, $1,491.82 is what you would get. Okay, so this also is not given to you. You're not likely to see this. Usually you're told a more finite number of compoundings that you have to figure out, but this is just in the situation where interest is compounded continuously. Okay, so we're not looking at a finite or a fixed number. We're technically looking at an infinite number of compoundings. Okay, so the formula is a little bit less complicated when we see that situation. Okay, and the last topic here, again, we're talking about applications of geometric patterns, is population growth. And I know we saw this when we talked about exponential growth in our previous unit, so this should be pretty quick and easy for you. So suppose we're talking about a population in a town, and we know that it increases by 2% per year. At the start of 1970, suppose we know that the population is 12,500. What's the predicted population in the year 2020? So we know that we have exponential growth. We know it's going to be a geometric sequence because it's growing by 2%. So that really means that the R value is 1.02, right? That's what you would multiply the previous term by to get the next term. All right, so let's think about what this would look like. So we have our starting amount of 12,500. This is going to look very similar to what we just did with our compound interest. So the rate is 1.02. All right, that's how much it's going to be growing by. Okay, and the power here represents the length of time that we want it to grow for. So where am I getting 50 from? well, the start of 1970 to we want the predicted population, and let's suppose it says at the start of 2020, well, that's 50 years worth of population increase, okay? So the power of 50, all right, is how long we want it to grow for, okay? So it's the number of years of growth, okay? So this, just jot it down, is the number of years of growth. So when we clean this all up, we get 33,644.85. Now we're talking about humans, we're not talking about dollars and cents. So to 3 sig figs, this would be written as 33,600. These zeros are insignificant. However, if you were to say 33,645, if you round to the nearest person, that is also acceptable, okay, for a final answer. IB would accept both. All right? That's all for now. Bye-bye.